So we've got, we finished up with this section, or with this portion, the last time that we got together. So we want to take a look at some perpendicular lines here in section 13. And the reason that these fit within the conversation on triangles is because the proofs for them rely on triangles. So now that we can prove it, we include them. And what I'd like to do is we'll talk about what the theorem is trying to say, but then we'll leave the proof that's there for you to read, and then we'll discuss briefly the next theorems and definitions. All right. So for this, right, we've talked a little bit about perpendicular lines previously, and so we want to make that conversation a little bit more formal here by saying that we can have the existence of perpendicular lines. So there's two ways that we typically encounter wanting to find or have a perpendicular line. The first case is if we're given some line L, so line L, and some point P on that line, then we want to say that there is a unique perpendicular line through the point P on the line. The other thing that we can have is if we have still a line, but a point Q that's not on the line, then we want to say that there's a perpendicular through that line and perpendicular to the line L. So those are the two situations. All right, and we certainly can say that in each case they do exist. And that's what the theorem is saying for us. The proofs for the first case, or the proofs are quite short. For the first case, it's essentially just the ruler postulate that gives us the entire thing. The second case, there's a little bit more to it. That's where the triangles become important. So, but it's still pretty straightforward to show the existence, and then the uniqueness of it is exercise. So I would encourage you and ask you to read through these, and if you have any questions, feel free to ask. But with that theorem, then whenever we need a perpendicular line, we can just say, one exists, and use that fact. So with the perpendicular lines, we can build up more ideas, such as the shortest distance. So if we were to consider, right, a line and a point, or you standing next to a wall, and if someone were to ask, well, how far away is that point from the line, or how far away are you from the wall? Right, you would measure that using a line that is perpendicular from the line, perpendicular to the line, and then the length of that segment from the wall to yourself. So this is the idea of a distance from a point to a line, and a little bit of language here to go along with it. So let P be a point not on a line L. If we let F be the foot, well, what is a foot? We're just saying that is the point where the perpendicular line through P intersects L. So let F be the foot of the perpendicular from P to L. If G is any other point on L, say over here, G, then what we get is a comparison of distances. This was the foot, this is some other point. Then the distance from P to F is less than the distance from P to G. And that's why we can say that the distance would be from P to F. It's unique. It is the smallest distance. Makes sense. So yes, what we've said is the definition that's here for a point P not on the line. The distance from P to L is PF, where F is the foot of the perpendicular from P to L. Exactly this image that we've drawn here. Excellent. Okay, so one more theorem for us to take a look at. A point lies on the bisector of an angle if and only if the point is, forgot to open my notes with all the responses in it. Yes, okay. So if and only if the point is equidistant from both sides of the angle. Excellent. So what we want to take a look at here is an angle. So let's say we have some angle, and we have, let's give some points on here. We're going to eventually want the bisector, so I'm just going to add that on here. And we want to show that P, a point P, is on the bisector if and only if its distance from the sides, it's equidistant from both sides, same distance. So let's give, let's see, oh, come on now. We'll add some points in. Wait a second. Then draw the other one. There we go. So if we call this A, B, C, the point P will lie on the bisector if and only if the distance, if it's equidistant from both sides. So let's draw the lines in that would make it equidistant as well, for that given distance. Those look like they could be about right. And of course, these are both right angles. Excellent. So this is the image that we want to use in our proof. So let's write up. The first step is to say that BP, right, we're going to assume a point lies on the bisector. So BP bisects the angle ABC. And that's given. Excellent. And the next step is to say, right, we don't have these other lines yet. We say P is on the bisector. So if we have this point on the bisector, we can create two lines, this one and that one, that are perpendicular to AB and perpendicular to CB, which we can identify based on the perpendicular existence. So we say, all right, well, we've got, let's let PF be perpendicular to BA. So we'll call this point right here, we'll call this F. So PF is perpendicular to BA. And let's let PG be perpendicular to BC. So that would give us this point here. Excellent. And these are perpendicular existence theorem. All right, so that tells us that since we have a perpendicular, we know that the measures of angle 3 and angle 4 here are right angles. So the measure of angle 3 is equal to 90 degrees, as is the measure of angle 4. And this is the definition of perpendicular. But since both angles 3 and 4 are equal to 90 degrees, we can say that angles 3 and 4 are equal to one another. So the measure of angle 3 is equal to the measure of angle 4. And while that seems quite trivial at this time, what this is going to allow us to do is to show that we have congruent triangles. So let's see here. If we can use, let's see here, we can't do side angle, that one doesn't work. But if we can get side angle side, or angle side, I believe, angle side angle, right? We've got some options on how we can show congruencies here. So that's what we'd like to do. We know that we have this side here is going to be the same. Since it bisects, this angle and that angle are the same. And we can get that 3 and 4 are the same. And once we have that 3 and 4 are the same and these two are the same, then we know that this guy and that guy are the same as well. And once we have all of those things, right, then we could use angle, side angle, and that would be perfect. So I think that's what we're going to try to do, if I remember correctly. Or sorry, I'm just taking a look here. Make sure I follow along. Yes. So it's not angle side angle that we use. It'll be angle side. So we don't have to bother solving for these ones. All right. So measure 3, angle 3 is equal to measure of angle 4. That's fantastic. For the next step, we can observe that these two, where did we go here? Here we are. These two angles are the same. So we'll call them angle 1 and 2. The angle 1 is congruent to angle 2. And this is because of the definition of an angle bisector. And this step here, right, was just the transitive property of equality. So we have angle, and we know that VP is congruent to itself. And that's by the reflexive property of congruence. Everything is congruent to itself. All right. So then we've got, right, we have angle, side, 3, 1, 2, 4, sorry, 3, 1 side, 4, 2 side. So we have that triangle. Let's see here, let's call it PBF. PBF is congruent to PBG. Triangle PBG. There we go. And this is because of angle, side with 4, 5, and 6. Excellent. Once we have that, we have that PF is equal to GP. So next step is PF is equal to PG, right? Distances, so no lines over top. And this is by the definition of congruent triangles. And once we have that, then we have that P is equidistant from BA and the BC. Excellent. And that's all that we were looking for. So we're just looking for the distance, and that's the definition of distance, 1311. Excellent. So that is finally the end of section 13.